Welcome everybody. It's a great pleasure to talk to you about speeding up robotics in conjunction with artificial intelligence. My name is Patrick Widler, part of the HSE management team. HSE is a system engineering company focusing on the automation of sample workflow and detection of nucleic acid, cells and proteins. It's a great pleasure to introduce Thomas Hanselmann, our head of algorithm and data analytics. Thomas will talk about the reference case where aspects will be highlighted when it comes to decisions on start from scratch or refurbish a laboratory system with our latest technologies. He will go through the major challenges, the decision aspects for everything new or retrofitting, and actually then use of artificial intelligence, success factors, and conclusion and summary. And Thomas, I would like to hand over to you, please.
Thanks, Patrick, for the introduction and welcome everybody. Out of all challenges, the biggest challenge is often to have a sound business case. Fast technological changes and complex interdisciplinary fields imply often large teams and complex decision-making processes. And this normally comes in conjunction with tight cost and timelines. How to square this circle? We show you an example of a laboratory robot for sample preparation demonstrating such a business case. An important aspect is the decision to make a new development versus retrofitting or upgrading an existing device. Everything new or retrofitting. This depends very much on the business case. For the presented study here, it was a clear retrofit of a successful device in the market, but with newly adopted modules to enable new IVD workflow solutions as well as to shorten processing times. It is important to outline potential solutions and address the following questions. What can you gain with what effort, costs, and risks? How can it be achieved? When will they be available? We demonstrate this on 3 parts of the instrument upgrade. Sample input, read 1D and 2D barcodes from given tubes and plate carriers. On the work deck, recognize objects like tip racks and tips, buffer bottles, and special trays. In sample output, we recognize a variety of labware cartridges from 24 to 96 tubes with 2D barcoded tubes. Exploring the problem space and having a broad view is mandatory. Think out of the box, build models, consider constraints, have backup solutions ready, and make sure each subsystem is better than necessary. This will rescue your project, especially when initial estimates were too optimistic without endangering the complete project. In our case, for an improved sample input camera based on 2D barcode reader, we modeled the optical key parameters to decide what kind of imager would be necessary with varying trade-offs, constraints of potential hardware, like frame rates, exposure modes, imager orientation, or communication interface. In such a project, make use of the most appropriate rapid prototyping tools, for example, MATLAB. Quickly show proof of working, or fail fast to search for alternative solutions, is adamant to reduce risk and cost. Rapid prototyping tools are not only tools in the software domain. There are also mechanical prototyping kits that we have used for camera stands and different kinds of illumination panels, with which development turned out even faster than with 3D CAD models and 3D printing. Make sure your algorithms are generic and model-based designs are preferable. Avoid the use of ad hoc designs and if-then-else code. This inevitably leads to unmanageable spaghetti code. Here, I want to give you an example of the MATLAB rapid prototype visualization, which we used from a very early stage on. The large window on the right side shows the tracking of rack ID and positional barcodes. On the left side, there is a 3x3 grid displaying on the middle row the current frame, on the top row the previous frame, and bottom row left velocity and speed estimates, in the middle barcode positions and possible aliasing events, and on the right a movement criterion, indicating whether the rack is inserted or stationary. On the top row right, we show image acquisition timing on the camera, as that caused a lot of trouble at some stage in the development, as the camera took double or triple the amount of normal image acquisition time. This issue was quickly discovered and mitigated within 1 day by extending the dynamic movement model, incorporating non-constant frame rates, whereas finding and fixing the bug causing the issues on the camera took over 4 months. The model-based design saved the project and let us continue despite the otherwise game-stopping bug. Here you see a tube rack being inserted. First, the rack barcode is identified and tracking is initiated, and then positional barcodes in red are being tracked. In the lower left corner, you see the blue line indicating the velocity, which takes on a sinusoidal form over tracking time. This means the rack is being pushed in and then reversed out before finally pushed in again. Therefore, it can handle a non-constant insertion far better than the previous instrument, and besides, it can decode also 2D barcodes on tubes. On the top right corner, image acquisition times are plotted, and towards the end, the frame acquisition bug appears. Robust designs on components and module level are important and make your modules more reliable. Whenever possible, make use of supporting hardware that can simplify your implementation. For example, in the workdeck, we use strong top lights to lessen the influence of potential ambient environmental lights and use the background illumination to make it easier to detect absent tips. For sample output, we designed special illumination panels that allow for homogeneous and diffuse illumination to avoid hotspot speckles that would occur with discrete LEDs. Similarly, in sample input, we use the diffuse illumination with the camera looking through the illumination panel. Another way to achieve robust designs is to use generic solutions and parameterize these, as we have done in sample input. We track only positional barcodes and parameterize the relative locations of other barcodes with respect to the positional barcode. This allowed to use a tracking code for 2 completely different racks, a tube carrier with 24 tubes, potentially with adapters to account for different diameters, and a well plate carrier with space for up to 4 well plates. We used off-the-shelf cameras, but custom adapted for our smart sensors. You need a competent and committed sensor partner. Per instrument, we use 3 cameras of the same model type, but with problem-specific imagers. This yields a much better buying power due to larger numbers. Let's have a look what is meant with make use of state-of-the-art AI. So what is state-of-the-art AI? Good engineers that know the methods and use them appropriately, not with a sledgehammer based on buzzwords. Everybody speaks about deep neural networks. Yes, they're powerful, but do you need them in every project? Do you have enough data to train them reliably? We almost succeeded with smart engineering approaches. Well, we seem to be just in specs, but remember, we strive for the extra bit to achieve robustness in the field. But on the workdeck, we came to the limits of traditional vision software with easily parameterized low-level feature detectors. Accuracy and maintainability of scripts, the programs that run on camera, come to their limits. But we selected a great camera with a powerful Linux OS, FPGA supported, SIMD capable. If necessary, we could use the deep neural network or fast decision tree detectors to have a more modern recognition software, like custom-made, specially trained tip detectors. Here, our strong partner is supporting us with a custom-made tip recognition solution, as a future-proof backup solution. So let's look at some benefits of the presented approaches. Retrofitting often leads to shorter time to market, less risk compared with completely new development. Testing of a novel solution step by step, possibly already against some known reference solution. Exchange or add new functional modules. Time delays for developing an exchange solution are less critical. For our work deck, it was possible to use the previous slow laser scanning solution for the software team to develop the new instrument software without much impact. Cost neutral, but it really depends on many constraints. For example, stakeholders, markets, users, availability, instrument type, and competitors. Generally, retrofit solutions are beneficial in the short term, neutral in the midterm, but possibly more expensive in the long term. What were the success factors? Success factors were clearly the broad and interdisciplinary engineering groups that include mechanical, electrical, and software engineering, as well as physics and optics, and also broad knowledge of biological workflows run on such instruments. Infrastructure with our own workshop helped to quickly implement and test ideas. Also close by specialist companies that could quickly do, for example, some laser cutting was very helpful to keep the project timelines. And last but not least, a great partner network where Chadak and Novanta company deserve some great credit. And of course, MathWorks that develops MATLAB and other companion tools, setting the state of the art for such engineering tools. MathWorks also has recognized HSE as a competent user of their tools and admitted HSE into their service partner program to support other companies. Conclusions and summary. In this webinar, we presented a case study of retrofitting an established laboratory robot, addressing faster turnaround times and enabling IVD workflows by allowing tracking of barcoded tubes. Key factors addressed were time to market, limited resources like engineers, budget, and time, but without compromise on performance and to achieve high instrument reliability. This concludes this webinar, and we would like to thank you for your attendance. If there are any further questions, please do not hesitate to contact me.